What's up? Welcome to today's live stream. It's a Sunday stream. I know I normally don't do stuff on Sundays, but I'm on vacation, so yeah, I'll do what I want. I am going to go to there's an eclipse happening tomorrow here in Texas, and I had planned to drive out to go see it because it's not far from me. So as a result, I probably am not going to stream tomorrow. So I was like, let me just do it today. Yeah, hopefully all has been well with all of you. I know it's been a while. I've been very busy at work, trying to get these documents written. Got it to a point to where they are ready to publish, but you know, I'm going to hold off on publishing them until maybe the week after next week. To address some feedback items, as well as to give more people the chance to review, even though it's been ready for a little bit of time at this point. But yeah, I don't really have an agenda today. So either some folks are going to start saying words and we're going to make this an interaction, or maybe I'll just get bored out of your mind, watch me like edit some photos or something, edit videos or do something like that. I don't know. Anyways, let me go ahead and hop into the screen share. And as you can see, I have nothing on my screen. It's literally empty. And yes, my screensaver is literally black, or my wallpaper is black, I should say. Let's see what's happening in the world, though. Let's see what's happening in my world, which is the tech world. Mixture of depths, dynamically allocating compute and transformers. Okay. So this is some new research for, I guess, for allocating where computation should happen for a transformer, like it's not a model. What do you call that? It's the technique. It's like the thing, the transformer, right? Do we know what the transformer is? Transformer, Cornell University. Yes, this is the paper right here. Attention is all you need. Just a little bit of attention. So this is the paper. I want to say that that defines what a transformer is, if I'm not mistaken. Yeah, let's go here. Where they go to the proposal. In this work, we proposed a transformer, which is a model architecture skewing recurrence. Oh, okay. So we're no longer using recurrence. Okay. All right. And instead relying entirely on an attention mechanism to draw global dependencies between input and output. And it says that this model allows for significantly more parallelization. Yeah. So this, I want to say, it's the thing that's powering like these transformer things here. But let's see what this is. Read it. At least abstract. Transformer-based language models spread flops uniformly across input sequences. These are floating point operations, for those of you not in the know. In this work, we demonstrate that transformers can instead learn to dynamically allocate flops to specific positions in a sequence. Okay, interesting. Optimizing the allocation along the sequence for different layers across the model depth. Our model enforces a total compute budget by capping the number of tokens, K, that can participate in self-attention and MLP computations at a given layer. All right, the tokens to be processed are determined by the network using the top K routing mechanism, which K is defined as a priori. This simple procedure uses a static computation graph with known tensor sizes, unlike other conditional computation techniques. Nevertheless, since the identities of K tokens are fluid, this method can expend flops non-uniformly across the time and model depth dimensions. Let's see what they're over here talking about. So yeah, I want to say this is what we were just reading, the abstract. Introductions. Not all problems require the same amount of time or effort. Thank you for wasting my time with this sentence. It's like obviously. Analogously, if I can pronounce words. In language modeling, not all tokens and sequences require the same time or effort to accurately make a prediction. Yeah. And yet transformer models expend the same amount of compute per token in a forward pass. Okay, I see what, okay. I see what problem they're solving now. Yes, so irrespective to the input, everything is going to get the same amount of computation resources, even though not everything requires it. Yeah, this right here is, yeah, all right. Anyway, ideally, transformers would use smaller total compute budgets by not spending compute unnecessarily. I wonder how they're modeling this cost of compute. Let's look at a picture. I hear those are worth 1,000 words. Do we get 1,000 words out of this picture? Okay, so I wonder if they're just taking like this MOE, which this came out, you know, I guess it's relatively new. It's not like it just got dropped or anything. Oh, my bad. I just see there's a message here. Let me pop this up. You planning on putting out an Eclipse video with your cameras? I feel like I'm there. No, I was not. I was planning to enjoy my once in a lifetime experience without trying to look at a screen. Additionally, if you've ever tried to do any type of like moon photography or solar photography or astrophotography, you know that you need specialized equipment. It requires planning, and yeah, you wouldn't be able to see the eclipse with the lens that I would bring if I would have brought my camera, like that particular camera. I will be bringing my Fuji X100V, but that's a 20, I mean, it's technically a 35 millimeter equivalent focal length. You're not going to see anything with that. And if I would have brought my Sony, I would have brought the same kind of lens, like a 16 to 35. And again, you won't see anything with an ultra wide angle lens. So it's not even worth the time or effort. No, I'm going to spend my 3 minutes of totality looking at the thing that, like, you know, our ancestors looked at. Yeah. Let's see here. Mixture of depths transformer. Wait, what the hell's a MLP? I don't know if I know what this is. It's an MLP. Yeah. Oh, it's a multi-layer perceptron. Oh, okay. All right. I don't know. We call these MLPs now. Sure. Get my notes out just in case I need to learn something. You know, you never know when you're going to learn something. We don't care about that right now. Okay, so we get XI and then the next X or the next input, and we're gonna route it. Oh, okay. So I guess this right here is a router. Okay. So now I guess we're gonna have to figure out, well, how do we route? Like what function do we use to route? Is it like a mathematical type of thing where we're doing some type of comparison, or is it based off of some heuristic, or is it based off of some pattern? I don't know. I guess we'll figure that out at some point in time. This W equals 0.141. I think this could be a weight, given that, well, yeah, I'm gonna call this a weight. Although I can't really know. I really don't know right now. Yeah, we're gonna route it to somewhere, and we're either gonna route it to this. I don't know what self-attention is, but we're gonna normalize it somehow. Or here. All right, I think I need to read that. See what's really going on. Okay, so figure 1, as a mixture of experts transformers, we use a router to choose among potential computational paths. Oh, okay. So they're saying that this is the same. So it's building on top of this MOE. Gosh, I think Mixtral is an MOE, if I'm not mistaken. Mistral. No, go away. Let's see here. Mistral model. Sliding window attention. Okay. Is it not a MOE? Mixture. All All right, so we'll see. Is Mistral a MOE? Yeah, okay. So, yeah, I think it is. It's a sparse MLE architecture. Okay. Oh, I see. I got another message. I got to drive to Illinois for the closest place to see it. I'm going to miss it. Where do you live at now? I thought you did. Aren't you in like? Wait, did you say you're in St. Louis or something like that? Don't listen to me. I don't know. But hey, if you gotta drive somewhere, just drive. Like I gotta drive somewhere too. I'm driving to either Austin area or San Antonio area, and that's, I mean, both are like 3.5 hours to the respective areas that I'll probably go to. At least for Austin. If I do San Antonio, it's like 4 hours. Oh, you're in Minnesota. Okay. Yeah, so it's like I got like a, basically a 4-hour drive ahead of me, and that's assuming there's no traffic. I've been hearing that there's going to be stupid traffic, and I don't know, maybe, yeah. This is going to be my first road trip in an EV, so good luck to me. Oh man, I went to the dealership the other day. I think this was Saturday or Sunday. What's today? I went on Friday. I tried to order another G-Wagon, and they're like, orders have been closed for 2.5 years. I was just like, I don't care. Like, I need another G63. So yeah, they're just like, they still didn't like allow me to purchase an allocation, but they did say, hey, we'll put you on a list, but like, no, don't get your hopes up. So yeah, I don't have a good mode of transportation, unfortunately. And the Tesla's fine so long as I'm doing my daily, just what I do around town, which is farthest I drive is maybe 5 miles away. But yeah, I'm not looking forward to this drive to San Antonio. I was contemplating renting a car, or San Antonio, Austin. I had to go the same direction. It doesn't really matter. But yeah, I was thinking about renting a car, but then I'm just like, the car rental places don't have nice cars. Like all they have are just like cars that I wouldn't drive. So yeah, I'm gonna take the Tesla, and maybe I'll have to push it. We'll see. Maybe I'll learn a lesson that I should just take whatever the Ford Focus bullshit that they have at Hertz. I did look for the luxury of the premium cars, and the only thing they had were like a Cadillac. And I'm like, is that premium really? A Cadillac? Like a Cadillac XTS. Let's see, Cadillac. I think it was some type of SUV looking thing. Oh wait, yeah, no, it was this. It was this. This is the car that Hertz says is a premium car. This car. This is premium. And I'm saying Hertz because Hertz is literally across the street. I'm lazy. I don't want to. Like, I can literally just like walk across the street under the bridge and go to the Hertz. The alternative is to go all the way to the airport, one of the airports, which are both far as fuck, and I don't want to do that. So yeah, anyways, enough of my complaining. All right, so but unlike in MOE transformers, the possible choices are a standard blocks computation. I see what they're doing here. Okay. All right, so i.e. self-attention and our residual connection. Since some tokens take the second route, mixture of depths. Wait, is this new? I've never heard of a mixture of depths. Is this what they're? Oh, this is what they're introducing. Okay, all right. I was like, wait a minute. I've never heard of a mixture of depths, but maybe that's why they're introducing it here. So mixture of depths, transformers have a smaller total flop footprint compared to vanilla or MOE transformers. On the top right is depicted a trained model's routing decisions for a short sequence truncated to 64 tokens for visualization purposes. And examining the choices, one can find tokens processed by later blocks layers despite passing through relatively few total blocks throughout the model stack. This is a unique feature of MLD compared to conventional halting-based or early exit conditional computation, which instead engage blocks serially, or vanilla transformers, which engage everybody. Okay. So here, how are these two things different here? Oh, I see what they're doing. So they're saying with this weight, it's going to get routed to whatever this is over here. And then with this weight, it gets routed to whatever this is over here. Now, what's not clear to me is, are we still going through here in addition to, like, are we doing like a parallel pass? Did it say that? Did it literally say those that, like, say that in words and I just didn't understand it? Anyway, I'm just going to trust my gut. My gut is telling me that we're sending this input X with this weighting to both this particular, I guess I'm gonna call it network, I don't know what it is, and this network over here. Again, I don't know what that is either. And we get use block, route around block. Okay, routing decisions. It's cool. Implementing mixture of depths transformers. The strategy is set a static compute budget that is less than that of an equivalent vanilla transformer by limiting the number of tokens in a sequence that can participate in a block's computations. I wonder if this is reset each epoch, or is this like for the entirety of the training? For example, while a vanilla transformer might permit all the tokens in a sequence to participate in self-attention, we might limit the number to 50% of the tokens in a sequence. Use a per block router to emit a scalar weight for each token, which expresses the router's preference for that token to participate in a block's computations or to route around it. And identify the top K scalar weights per sequence per block to select those tokens that will participate in a block's computations. Since precisely K tokens will participate in the block's computations, the computation graph and tensor size remains static throughout training. And it's merely the token's participation that's dynamic and context sensitive. Okay, we then discuss some complications when sampling post-training. All right, so they go into how to define a compute budget. I wonder if they have an associated paper with, or I'm sorry, associated implementation. Token choice routing. Okay. Expert choice routing. Or we can do this expert choice MOD with self-attention and MLP. Oh. I think I kind of see what's happening here. Or maybe not. Maybe not. Maybe I don't fully understand yet. All right, so we'll see XILI, and that's going to be, so we get two things. So it'll be XIL, whatever that is, that term is, if RLI, the sub I, is less than whatever this thing is. I'm assuming this is a cost, or like some type of, this is the thing where I'm like, we need some type of function to compute a cost to determine, you know, like, are we going to go less than? So here we are. We do have that relation. Anyway, I see we have a question maybe. Rental car options really do suck. I think they've gotten worse since COVID has happened. Yeah, I felt like in the past there used to be more options when it came to renting cars, both in terms of companies as well as potential vehicles that you can rent or lease or whatever the word is when you get a car. And yeah, it just seemed like, you know, now we just get like just blah, just I don't know. The fact that rental car companies are looking at a Cadillac XTS as a premium car, maybe, you know what, maybe, what the hell is a premium car? I don't even know what a premium car is anymore. We'll say segment. Maybe Google can figure out what the hell. Yeah, what's the difference? Because like, I don't know. I thought a premium car meant good car. I didn't know it meant like Cadillac XTS. That's what I thought. Let's see. Luxury cars is one. Wait, what does it say? It offers passengers immense comfort and convenience. Every luxury car will provide the buyer what they want. No, that's bullshit. Not all are spacious, as some are used. Man, did a kid write this? I'm not reading that bullshit. Premium car lies between luxury and an affordable car. Typically they appear, what the fuck is affordable? Affordable, like, literally everything is affordable if you manage your money, right? So it's like, what the hell does affordable mean here? Anyway, they appear and perform much better than an affordable car. Hence the higher price point, okay? They are typically four-door saloon, rides are larger. Hat sets them as, okay, I'm not reading this shit. This is trash. Wait, is there premium in here? Premium. Is that like a real thing? Yeah. Acura. Okay. CLA. Oh, these are considered premium cars. Oh, okay. Interesting. A4. Interesting. All right, sure. I guess I just learned something. I would not consider none of those cars premium or luxury, but you know, I am happy to be wrong here. It's not a problem I have to deal with though. I'm going to take the Tesla, unfortunately. Hopefully I get there. I'm going to charge it tonight to not 100%, but maybe 95%. And I'll probably stop at the Buc-ee's that I would normally stop at anyways and charge up there. And hopefully, you know, I can make it to wherever I need to go. Because once I get past that Buc-ee's, I don't think there are many superchargers. Let's see. Tesla. Supercharger. For what it's worth, this will be the first time I've ever left the city. In fact, like on this Tesla lease that I have, I get 10,000 miles a year for the lease. I've had the car for over a year now. Guess how many miles I've put on this car? I have 3,400 miles on my Tesla. So that should tell you that I rarely drive it. So I'm not used to having to think about like, all right, well, how am I going to get, wait, how do I even see this? Like, this is useless. I'll need to be able to see like where the fuck these are. How do I see that? Tesla supercharger. I think that's how you spell it. Wait a minute. Wait, what? Oh, wait. Wait, hold on. This can't be right. Wait a minute. Hold on. This can't be right. Are there really no superchargers? All right, what if I say San Antonio? How about that? My friend lives in San Antonio and he has a freaking Tesla. So it's like, yeah, okay. Yeah, this is the one supercharger. This is my one opportunity in between where I live, which is way the hell over here, and where I want to go, which is way the fuck over here. So I have this supercharger. I'll probably have to top up somewhere in Helotes or near Bernie in San Antonio. And then I can go on to where I need to go. But I can't go too far because I need to make sure I can get back to that same charger so I can charge up, so I can make it to this charger, so I can charge up, so I can come back home. It's gonna be a fun day. My rental options were a 1980s scooter or a horse and carriage. I don't know. Wait, when was this? You can't be that much older than me. Like even my stepfather, who's much older than me, like, you know, he was renting cars. And we down here in Texas where we actually have horses, and we not renting horses out here. The only horses we have are under our engines, and you know, at this point, I'm working with a lot of horses. Except they're Tesla horses now. I fucking hate it. I'm trying to get something else. I have my spec, for the new G-Wagon that I want. I don't know. Who knows? Maybe I'll just move to a carless city, like somewhere where I don't have to have a car. Outside of America. Obviously, I'm not living here. Like somewhere else where I don't even need a car, because there are just not that many good cars now. I've had most cars, and I have a rule where I don't buy the same car twice. And there are technically 3 cars now that I'm on where I'm like, yes, I'm going to break the rule, but they're different generations. So one is the GT3. I can't buy another 991.2. I bought 2 of them already. I can't do another one of those. But the new 992.2, if they do that, I could do that, because it's even though it's the same car, it's a different generation. So that's my loophole. Same with the new G-Wagon. So the new 2024, my buddy, like, he just sold traded his 21 or 2020 or whatever for the new one, which is the same. I thought it was the updated one, and yeah, it's the same one. And I'm waiting. I'm like, all right, I need the 2025. Whatever has the new MBUX system, whatever has the new steering wheel, the new command interface. That's not the one from the C class. And it has that new EQ system, which I'm really excited about. I'm very excited about that, actually, like more than you may think. Especially now that I've had an electric car, I'm like, yes. Like if I can get that same type of power delivery, but in a G-Wagon, but still have a V8, oh my gosh, amazing. You don't even understand. It's just amazing. G-Wagons have turbos, so there is a little bit of turbo lag, which is why I'm like, yes. Someone coming from like naturally aspirated engines, I'm used to, I tap the gas and something happens. With the G-Wagon, you tap the gas, you wait a little bit, and then something happens. With this new EQ system, my hope is that when you tip in on the throttle, you get immediate response, just like in an electric vehicle. That's one thing I have to admit, like I was very much against electric vehicles, but when it comes to power delivery, there is no internal combustion engine that can compete. None. And no, I'm freaking not like Jeremy Clarkson or anything, but I've driven enough cars to have like I think I have a lot of experience to say that like there's nothing that beats an electric power delivery. But the sound sucks because there is none. Anyway, let's go back to what we were reading about implementing our router. So they're actually going to go over the implementation, which is kind of cool. So yeah, let's go over it. So as a reminder of the high level intuition, each token is processed by a router to produce a scalar weight, and the top K weights are then used to choose the token identities that will route through a transformer's blocks, which comprises self-attention and subsequent higher gain. So suppose we have the set of token embeddings and the sequence of lengths S for a given layer L. That is X, L. I don't know what this X superscript L is. I wish I can say I knew that. I don't know what that is right now. All right, and then we get this XLI, where I is an integer between, is that I is greater than or equal to 1 and less than the length of the same. Okay, I guess I understand what's going on here. So effectively, we're indexing it into an array. This is kind of how I'm interpreting this, but maybe I'm wrong. The router's weight for a given token embedded in a scalar produced as a result of the linear projection. Is this, oh gosh, what's this one? Is it like it's not sigma, I forget the name of this. Something theta x something, yeah. So we're just going to multiply this, and I'm assuming that this x is a scale. Wait, is the x a scalar value? Did it say that? This is is this a lowercase x or big X? This looks like a small x, so this must be an element out of the set x here. Yeah, see XL right there. So XLI, so this, whatever this, at this index of x here. So this x is a vector. I'm assuming it's a vector. We're going to index into that vector, pull out that value, and we're going to multiply it by this weight right here of, I don't know where this theta term is coming in at, but we'll figure that out. Our goal is to use these router weights to determine the output of the block's computation of each token. Suppose probability beta, whatever this is, RL is the beta's percentile of the set of router weights. Okay, so we have our set of router weights where beta equals 1 minus C over S. 1 minus C over S. Is this the cost? Oh, never mind. And C is the user-defined capacity per batch element. Okay. An integer, wait. An integer under S that defines the number of tokens from the sequence. Oh, okay, this is going, okay, all right. So this right here is going to be smaller than the length. So it can never be the length. It always has to be one less. So this must be like a way to index into something. All right, and then a block's output for a given token is out of this X set here. We're going to, I don't know, I would probably run like a map or something like that to produce a new list and run it through whatever this computation is. We're right here, right there. So we're going to return whatever that value is. Wait, hold on. Oh no, I lied. So wait, L plus 1. This is confusing to me right here. I would have expected this to be the plus 1 part. Like this XL, and then this would be XI plus 1. This XL plus 1. This is, I don't know if I understand that one. Let's see. Suppose we have a set of token embeddings in a sequence of length S for a given lay. Oh, okay. I forget we're dealing with multi-layer. Oh man, you know what? I feel kind of dumb now because it literally says it up here. It literally says it right there, MLP. I'm like, wait, and yeah, all right, there we go. I guess it does make sense that we'll have multiple layers and a multi-layer perceptor. Anyway, all right, let's see here. I'm joking, but yeah, I had trash options for rental. Nothing but clown cars. Yeah, what's up with that? Like, what? I don't understand. Like, I thought that these companies, like, they wanted money. Can't you charge more money for a better car? Like, for me, like I was looking for like maybe like a Porsche Macan, like a base Macan, not like a nice one, just like a base Macan, or maybe I don't know, like a freaking even a 3 Series. How about a 3 Series? I didn't even see that. Let me see. Let me look again. Car rentals. Let me just look at hobby. That's closest to me. Wait, HOU. Yeah, IH is too far. Like, I'll just straight up, I'll ride the bus before I drive to IH. Like, real talk. IH is, oh my gosh. It's almost like another city, even though it's technically here. All right, let's look for the freaking thing that I Googled. I literally said what I wanted, HOU, and it showed me everything but HOU. HOU is way the fuck over here. Why did it not do that? Anyways, let's go to my airport. By the way, now y'all know that I have an airport. You learn a little bit more and more every day. All right, 3. Yeah, we're not. All right, Enterprise. Here we are. Cool. I have like a status with Enterprise. That's the only reason why I'm. HOU. Houston Hobby. Exotics. Oh, look, okay. Never mind. Maybe I'll get an exotic. Yeah, we'll only do it for a day. I don't really need it for long. And I gotta take my dog too. That's the other thing. It's that like I also want. That's the other thing. I want to bring my dog. So I can get an X5, Range Rover, Velar, or a Macan. It's this or similar part that scares me because if I get there and they come here handing me the keys to some type of Chevy product or Ford product, I'm gonna have a problem. Cause like, you know, I don't care. I just don't drive those. And yeah, I guess I can get this, I suppose. I'm not gonna order this now. Don't worry. I'm just looking to see like what other information there is here. Monday, April 8th, 12. Okay, now obviously I need to get this early. I'm gonna leave stupidly early in the morning. Oh, look at that. I had to get it today. I had to get it today. All right, that sucks. Okay. Well, shit. All right, so we're gonna get it. Oh, I can't get it today. They're closed. Well, fuck. The Eclipse is at 1. It's a 4-hour drive. All right, I'm taking the Tesla. Fuck it. We'll just take the Tesla. No, I'll have to just risk it. I'm saying if they have an implementation up somewhere, that would be dope if they do. Now, I'm just looking at these notes here. Sometimes what they'll do is if they do have an implementation, it'll be linked kind of like in here. So I'm just kind of going through to see if they left any hints that, hey, yeah, we provided a reference implementation for this. Or hell, you know what? Maybe I can see if one of my buddies would want to implement this paper. All right, so I just asked one of my buddies if he is down. Obviously, I'm not gonna do it now, but maybe this could be something in the future where we implement this paper. And let's see, MOD reference implementation. No. Wait, what is it? Model of depth? I've already forgotten what it's called. Model of something. Maybe if I put MOD in here as well. And MOE, how about that? I'll put in MOE too. Maybe not. Unveiling the efficacy of foundation models for depth estimation, edge detection, depth intuition, analysis. Nope. Oh, it's mixture of depths. Okay, mixture. Okay, that explains it. Mixture of depths. Nothing. Oops, maybe if I spelled mixture, right? Mixture of depths. Here we are. Implementation of the paper, mixture of depths, dynamically allocating compute. Oh, look at that. We have 2 implementations, both relatively recently. DS store, they're on a Mac. Okay. And they Shell and Python. All right, let's see how they implemented this. All right, let's take a look at our main. What's this incident? Nothing. Nope. All right. Oh, this is relatively easy implementation. So they have their router. Why is this all commented out? Oh, they're not done. Okay. Or maybe they are done and they just have this old router. Okay. So they have a router and they have this forward pass, which takes in that tensor. Let's pull up the reference implementation at the same time. Wait, how do I close this? Oh, there we are. And we'll do this. I'm looking for the router stuff. Here, wait, no, this is a scheme. We don't care about that right now. Routing, here we are. Wait, I hear some weird sound. What's going on? What's that noise? All right, so it looks like when you initialize this router, like, why do we need dimensions? Is that, so I know we need number of tokens, because I think that's what they said. I forgot where it was. I should have highlighted it, but I didn't. There's a token limit, and then the block, which I guess where you're gonna route to. Oh, wait, shit. Wait, a block is just, oh, they're just nodes. It's just a northern, okay, I didn't know that. All right, damn, num tokens, limit percentage of tokens to be attended. Okay, token router predictor. Token predictor, token router predictor. Where is that coming from? Token router predictor. Oh, here. All right. A router to emit scalar weights for each token. All right. We take that weight predictor, or no, we're going to set a weight predictor, and that's going to be, and then linear. Is linear a linear regression? I don't know. I think this is TensorFlow. I want to say this is TensorFlow. Oh no, it's Torch. Oh, PyTorch. Okay, I don't know PyTorch, but that's okay. We'll say PyTorch docs. And the function is linear. And it's going to be here, this a lowercase linear. This uppercase linear is a class. And when I look at this, wait, where was it? Oh wait, oh no, maybe it is this. I don't know how import works in Python, but maybe this NN is going into this thing here and pulling out the class. So maybe I do want this top linear, or this, not top, this linear here, maybe. All right, linear module attached with fake quantization module. So wait, okay. Used for quantization aware training. All right. Wait, why are we quantizing? Did it say we need to quantize? Or is that just normal to do? All right, I'm just gonna assume. Actually, I'm not gonna assume. I'm gonna ask ChatGPT. How about that? Quantization when training a technically is any model. It doesn't matter if it's LLM or not. We'll call it an NN model. How about that? Sufficient computational resources, yes. Real-time inference is not required. Okay, all right. I think this is the one. All these other ones are irrelevant, like obviously. Model, obviously. I'm gonna say obviously. I don't really care about research. Like, Harper says, okay, so this is the one. This is the answer. So if I'm not needing to do real-time inference, then I don't need it. So it turns out that because we are doing real-time inferences, we do need that. All right, that's good to know. So linear, I wish that I can see like an image of what, like when you initialize linear, like what does that look like? Do I have PyTorch? I probably don't. Let's open up a new thing, and then we will do conda activate base, just regular. Maybe it'll figure out. Wait a minute, whoa, something's going on. My shell never opened. What's going on with this? The hell? Uh-oh. This isn't good. My shell isn't launching. But this shell launched. Whoa. What the fuck? Why? Okay, fine. I don't know if I care anymore. We'll just activate my base thing right here. And do I have PyTorch? Conda. I don't know how to tell what I have installed, so we're just gonna have to ask for some help. List. Oh, that's too many. Let's see if go away. Fuck. All right. Let's see if we have some PyTorch action in here. So we'll say PyTorch. Oh, look at that. I do have PyTorch. Okay. So with that, I guess what I can do is test something out, I guess. We'll put this on my desktop. All right. And what was it? Import something, pie something from Torch. I don't know. Torchies, tacos. Was it Torch? Oh, this one. Wait, from Tensor. Wait, from Torch. Oh, okay. No, okay, I'm done. All right, I'm stupid. What the fuck? All right, so we're gonna do that, and then I want to create this. Basically, I want to see what this thing is gonna emit, because I don't know what the fuck this linear is. Like, what the hell is that? I don't know. So we're gonna figure out what that is. So we're gonna do. We'll just say NN, oops. Wait, what? We'll call it A and we'll say NN dot linear. And we'll say dimensions 1. So I'm assuming that this is saying that I want a vector, because it's saying this dim here, which is passed in. So I'm assuming that dim is a number. So let's just give this a 1. Let's just say 1, 1. That's easy. And then how do you print? Is it just print? Maybe. Wait, how do I run shit? Is it just conda run? I think it should be conda run. And we'll go to whatever that test is. Error, conda run, failed, C above error, permission denied. Wait, what? What do you mean permission denied? Do I have to make it executable? I don't think I should have to do that. Let's try running it on the Python. See what happens. Oops. Well, before we run it on the Python, let's just go to my desktop. That'll be easier. Try to run it there and we'll say test. Linear, okay, all right. So linear, in features 1, out features 1, bias true. So it has its own printing thing. So what, okay, all right. Let's do that. Okay, let's see what happens if I make this a 2. Is this the in features? I have a feeling it is. Oops, fuck. Oh, okay, sure. I guess this is a new session. I don't know why I would expect my previous command to be here, but we're going to run Python 3 tests again. And yeah, cool. So now we get out features 20. I mean, it was, yeah, all right. So it seems like this first one is in features and the last one is out features. By is true. So this is interesting. So here's what, let me open up a thing. Okay. There's a way that you can do, is it latex? I don't know how you do latex in here. We'll just do this. So B is, or bias is our whatever. But we're also gonna have a weight. You know what? I'm gonna keep it as W. We'll have a weight times our X plus a bias. Right, so that's what one of these things was just talking about. I saw it somewhere. Wait, oh, I'm tripping. I know where I saw it. I saw it in my code. It's literally the thing that I'm doing. Did I quit Visual Studio? I did. Oh wait, no, I didn't. I never had Visual Studio open. I'm dumb. I had it open here. Yes, so here, when I saw this bias equal true, what I was thinking of, I'm like, all right, well, could this be like the same thing as this right here, where it's like you have your weights, you have your inputs, X, so X would be a big X, you know, you'll have X, and then you have like an X, lowercase x, I, which would be an element of X kind of thing. It's a vector. This weight right here is also a vector, this right here is also a vector. And this bias right here is, it's just something else. You can think of it as like, it's all linear. You can think of it as like moving it up and down. You can think of it that way if you want, or not. You can not think of it at all if you're into that. I like not thinking of things. It's awesome. All right, let me make sure. Yeah, in features, out features, bias, true, which is its default. Linear model attached with fake quantized modules for weight used for quantized aware training. We adopt the same interfaces as torch, n dot linear. Wait, what is it? Is torch and PyTorch different? I'm gonna assume that is torch. I thought torch was PyTorch. Yeah, whatever. All right, so these are basic building blocks for graphs. We have containers, a convolution layer. Oh, that's cool. So you don't have to implement your own convolution. Although it's not that hard to do, to be honest. Pooling layers, pattern layers, nonlinear activations, latest sum nonlinearity. I wonder if this is like ReLU shit. Like, is it like ReLU? Yeah, ELU, yeah, that shit. ReLU, there's probably like a leaky ReLU sigmoid. Yeah, it's all in there. Okay, dropout layers, sparse layers, distance functions, loss functions. What loss functions do we have? We have cross entropy loss. Okay, I know that. We have Gaussian. Any other? I don't know any. Oh, a soft margin loss. I didn't see soft max though. I would have expected to see like soft max here in this line linearity. I see the leaky ReLU right here. Where's soft max? I'm surprised there's no soft max. I see soft plus. I see soft shrink. I don't see soft max. There's 10H. Like what? Okay. All right. Is there something better than soft max? Oh no, here we are. Yeah, here you are. Soft max. They have it. Nonlinear activation. Oh, it's on the other. Okay. I'm like, it is a non-linear activation, but I guess it's not weighted some non. Okay, I see. Fine. Okay. So, if I'm not mistaken, if I'm not mistaken, this code here has just created. This is gonna be really hard to. I'm not really visual, but I'm gonna try. How do I do Excalibur draw? So I think what I've effectively built is this right here. Maybe I can make it straight, maybe right there. All right, so I have my two input. So we can call this like, I don't know. I'm gonna call it I0. How about that? That's a good name. Good enough for me. I0, and I'm gonna do like to make it like underscore. Like that means it's below. I don't know how to make it not in this whatever. And then this is gonna be I1, and then we're gonna have an output layer, or an output rather. So that's what I'm assuming that this is building for me. And this bias right here, you know, obviously that would be part of this activation. And we would more than likely have a weight right here, if I'm not mistaken. So we'll probably have like, I call it W. It's technically not W. I forget what you call it. I'll figure it out in a second after I do this part right here. So we'll do that. So we're gonna have our weights, and these are the things. These are parameterized, so these are the things we're really trying to find. Our bias. I want to say we can also backpropagate that. Maybe not. Let me see what this. Let me see what this is called. It's gonna annoy me. Greek letters. Where is it? Wait, seriously? That wait. Okay, here it's omega. Okay. Here we are. It's little omega. That's what that is, the W. Yeah, obviously I know capitals, but I don't know lowercase all the time. So it's like I know it, I sometimes know it when I see the capital, or I'll know it if I see the lowercase. And then I'll be like, oh, okay, yeah, then I know it. So yeah, I forgot that. Yeah, that's lowercase omega. All right, cool. So that's what we've just built with this linear thing. I think. I'm assuming. I don't know. The doc should tell me, but it doesn't. Shapes are really important in when dealing with this type of stuff. So you think that they would be like, oh yeah, here's, you're gonna get this thing. It looks like this. Anyway, so we get this, whatever this thing is, this linear model that allows us to do all of these things, which is quite useful because normally you do these yourself, like you implement all this yourself. All right, let's go back to his code example. Maybe. Did I close it? Okay, I guess I closed it. So the predictor is like, we're going to create the model up front and then we're going to do our forward pass. X is going to be is 2 inputs because remember there's 2, right? Well, at least mine is. We're going to have the batch size and the sequence length. Wait a minute. I'm trying to figure out where this sequence length is coming from. like where the hell did that just come from? This right here. Or are they just saying that this is what we're going to get? This is what our vector looks like. If that's what they're saying, all right, fine. So I'm assuming that's what we're going to get a vector where our prediction is going to be based off of these inputs. Yeah, that's obviously it. They have it here. So X is the batch size, the sequence length, and whatever dim is. So I'm going to assume the dimensions. So we have here is batch size, sequence length, and 1 hard coded. Oops. Wait, how did I get to here? Okay, so we do this. We do the math. That's what this predictor is really doing. Is that we are going to do some math with it, and then we're going to get these weights. And I think we can do some math with the current one that we have right now. Not fancy math, just like basic bullshit. Okay, so let's do this. We need to make sure that this right here is fine. Why is my computer slow all of a sudden? Okay, interesting. Okay, so I need to give it an input with 2, like a size 2. Let's just give it a 0 and a 1 for now. And I'm interested to see what it's going to output. And we'll just print B. Traceback. Oh, okay. Must be a tensor. Okay. That's fine. I think that I can just say tensor. I don't know how you create a tensor. Can I not just pass tensor? Can I not just do this? Oops. Can I just say tensor? Like that. And then be like, here's the thing. And then can I do that? Okay, yeah, I can. Perfect. All right, and then we get a gradient function, which I'm assuming is the function that I can then call to do back propagation, maybe. I'm assuming. Again, I have never in my life used PyTorch. So, like, I only know this stuff from fundamentals. But I will say, just like knowing stuff from fundamentals, this is helpful because like I can kind of see how this is starting to fit together. It's not bad. All right, so we get a tensor and we get back here. And the reason why this is like a length of 1 is because my linear model here only has one out, like one output. So remember, essentially what I just said, I drew it. I maybe drew it a little bit poorly. Let me draw it a little bit better. Instead of doing those, let's do circles. I think that's what a lot of people think of as nodes anyways. All right, yeah, there we go. So this is what we've just built essentially. So we'll call this our out 1 underscore 1. How about that? All right, so if I wanted to build this network right here, for instance, and we'll just copy this a few times. Maybe. Seriously, like what? Really? Seriously? All right, there we are. Perfect, cool. So let's say, for instance, I wanted to create this network right here. Right, and it has these inputs or outputs. Then I would do 3 and I'm sorry, 4 and then 3. What's unclear to me right now is how would I create a multi-layer network using this particular framework. Obviously I know how to do it from a, just yourself, but like how would you do it using this framework or whatever? Normally your hidden layers, we're going to have a few more. I mean, it doesn't have to have it, it could be as many or as few as you want. But normally your hidden layers are going to have a few more nodes. And there could be as many or as few as you want, and they don't have to all be the same either. Like, no, I'm doing this, but it doesn't have to be. I mean, if I want, I can say, you know what, this is going to be our hidden layer 2, if I want. And then I can be like, all right, well, I have 3 classes that I'm trying to, like, let's say I'm trying to classify things and I have 3 classes. And then I can have my 3 classes. And then we can do this thing right here. This may be like common knowledge, but when dealing with these things, all we're doing is a bunch of pairwise multiplications. All right, so we're going to take this thing right here, the input, like there's an input here. Let me make a little bar. All right, and then on this side is our input vector. Right, so we're going to have our input vector, and then this is going to get blasted to all of these things over here with weights. So we'll say blast. Do some more blasting, and then we're going to do it like with whatever weights there are. So like obviously we're going to have so we'll have our weight 0 all the way to weight n minus 1, like so. All right, so we're going to do this. We're going to take whatever these are. We would probably have to convert it into some type of thing that can be computed, like with a number or something like that. And then we're going to multiply it by this weight. And then there's going to be some bias, and that'll determine whether or not this thing will activate. If it activates, it's going to send some stuff over to here. And then if this activates, it's going to send, and it'll propagate it. The forward pass, that's why it's called the forward pass. But as I was trying to get at, like, this is going to go to every perceptron in the network, like that. Like that. So this is going to be propagated and passed, like this value is going to be passed to all of these with some weight, some weighting. And we're going to do that with all of these other ones over here as well. So effectively, we're going to do a lot of multiplication. So let's say that I'm trying to calculate this node right here. Let's make this another color if I can do that, maybe. So let's say I'm on this node right here. I'm trying to calculate, all right, what should be put here? Actually, no, I don't want to do that one. Let's do another one. Let's do this one. I want to know what should be put here, right? Like, how do I know what value needs to go into here? Because remember, this is going into that node also. I didn't make it clear, but that's going to this node, and then that's going to this node, and then that's also going to this node. So all these things are going to the node with weights. So we'll say weights. I know this visualization is trash, but that's cool. I'm not a visualizer. You can go to school for visualization. All right, so we're gonna have some weights. And what we're gonna do is we're gonna do a bunch of pairwise multiplications. So assume that that this column over here is A. We're just gonna call it A for now for demonstration purposes, and this is B here. And we're gonna make it capital because this is actually a vector. That's important to keep in mind. So what we're gonna do is we're going to say, all right, we're gonna go A, lowercase a, which is coming from the set A of 1 or 0, the first element, times B, the beast thing legit. And generally, like, whatever, it's fine. And then we can do this 0 right here, and we'll just copy and paste. All right, so let's just say this is going to be A1, and then this is going to be AN minus 1, something like that. BN minus 1. All right, so we're going to take all these things, and then what we do is reduce that. So first we do like our linear algebra crap. I mean, it's whatever. And then we're going to reduce it. How do we reduce it? We just run it through a summing function. We're just going to summate it, like add it. How about that? It's this function here. That one. Well, anyway, the sigma, it's that one. We're gonna add it. We're just gonna add them up all together. This is a weighted sum. We're gonna do that, a weighted sum. Obviously, there are what do you call those things? Do I have math symbols in here? Of course I don't. All right, well, I can't give you the formula, but I can Google it for you. How about that? I can do one better. Google's always better. We'll say weighted sum wiki, and we'll see what weighted sum looks like. Oh, there we are. So this is what we're doing right here. Okay, I can't highlight it. Oh, I can. All right, here we go. It's kind of what we're doing here, right? But I think we're also normalizing it as well. So like we probably also have a 1 over n, or not a 1 over n, I'm sorry, like a 1 over some other term where the other term is defined as literally this right here. Essentially the same thing. Let's see, wave function. Okay, yeah, here's one with the weighted average. Yeah, so you basically just take the thing and you just divide it by that. Okay. Yeah, I guess they just have these different forms of the weighted whatever, but it doesn't matter. Let's keep moving on. Let's see what else we got going on. Okay, so we're passing in these things. So we're going to make a prediction based off of the batch size and the sequence length. And then we have our model of depth router, which, how are we routing? Okay, limit percentage of tokens to be attended to. All right, token limit. Oh, okay. I'm surprised. I would have expected this to be like a floating point value. All right, block token router predictor. Token router predictor. Okay. Oh, that's actually quite interesting. I see what's going on here. This is actually kind of cool. So we're using a neural network before we did, like, how do I explain it? Hold on. Let me finish reading through it. Maybe I don't know if I understand it enough to explain what's happening, but I think I understand what's going on here now. It's actually quite simple. It's just like add one layer of indirection, like one layer of abstraction gets you this. That's actually quite interesting. Get the number of tokens to be attended to. That's no tokens. That's going to be the self token limit times the number of tokens. Interesting. Why are we multiplying? Unless this token limit is a percentage and they're just not making that this is clear a percentage, but they say that this is an integer. All right, whatever. Maybe they're dividing it at some point by something. Let's keep going forward. We have our forward. Just going to return a tensor. It takes the tensor and which is x. Okay. All right. So we should just do the calculation at this point. So yeah, weights. We're going to call our predictor, the token predictor. We're going to give it our weights, or x, and then we're going to we print them, and then the weights Again, remember when I was like, it's just a reduce, just a summation. Actually, I don't know what the fuck this is doing. What the hell is this doing? Ops? I don't know what the hell this is. All right, we got to figure out what this is. It's part of PyTorch. It seems, honestly, it seems like it allows you to, God, it's almost like you're meta programming. Like this looks like an expression, right? Like we wait BSD and then whatever this D is and then min. So this must be like, this seems like a, God, what do you call that thing? Like, this seems like you specify the the computations that you wanted to do declaratively, and then it does it for you. So this almost seems like it's a helper that's doing this for you. Let's read what it's doing for real though. And we want to look for reduce. We'll make this a little bit bigger. Reduce provides combination of reordering and reduction using reader-friendly notation. So it is, okay, so it is reducing, all right? Examples for reduce operation. I just want to know, like, what are these parameters? Okay, so we get the tensor, okay? And then we get a string with a reduction pattern. So this is the thing that I need to know, like, what the fuck is a reduction pattern? Reduction, wait. Oh, the reduction. Okay, so either I could do a union, a callable. Wait, hold on. Union, string, callable, tensor, tuple, and one of the, oh, okay, one of the available reductions. So you get min, max, sum, mean, prod. What does prod mean? Case sensitive, alternatively, a caller. Okay. All right, so I need to figure out what is this right here, this pattern. Like, I don't understand this pattern. How does that work? And how do I learn how that works? Or do I just look at here and just be like, I get it. Let's see, perform max reduction on the first axis. All right, so we have X, which is a random matrix of 132, and I don't know what this 64 is, so it may be a 3, like a 3-dimensional matrix maybe. And we want to reduce, so Y is going to be equal to reduce X, TBC, BC. See, this is the part that I don't understand. Time batch channel, and then we just want batch and channel. So is this saying that in this case, T is the Y, and that the thing that we were reducing are these B and C terms, and we're going to reduce it by taking the max of that? Is that what's happening? Like, I don't understand this. I wish there were more information about this pattern. Like, that's all I need to know. It's like, how does this pattern shit work? Basics. Okay, maybe this is it. Let's see, let's look for pattern. Operation patterns are a reverse of each other. Repeat. Images, BHWC, BH, new axis, WC. New axis is 2. Reduced equals reduce, repeated, BH. But like, oh, it's saying that these are equal. BH, new axis, WC, BH, WC, min. I'm pretty sure I don't get that. I don't know what the fuck is happening with this. All right, well, whatever. I know what it's doing. I know it's reducing. I don't know how, like, I don't really know what this is, but like, I know it's reducing. And we're gonna get the min. So we're minimizing. All right. we're going to take the minimum weight of all of these weights. Oh, we're using softmax for nonlinearity. Okay. Apply softmax to get the routing probability weights is equal to torch softmax of those weights. I don't know what dim equal -1 is. Is this the same as a transpose? Maybe. Wait, is this really the same thing that I was just looking at? Softmax. Wait, why? I don't. Oh, here we are. Dim int. A dimension along which softmax will be computed. So every slice along dim will sum to 1. So what does -1 mean? I gotta admit, I don't understand why the dimension is being set to -1 here. I'm sure that, you know, there is something that is doing. If I knew this library, it would be obvious, but I don't know. And this is just a magic number. Like, what does -1 do? We can kind of figure it out. Oh shit. Oh shit again. Oops, again, shit, god dang. Yeah, well, we can kind of figure it out, I guess. Let me get rid of this, close that. Do I need to import that? Torch. I think I do. Yeah, import torch. Shit, why did it fucking still here? Import torch. All right, so we have B here. Let's just do a C. How about that? Oops. Wait, what did I just do? How did I just screw up? What did I just fuck up? Just delete that line. We'll put a new thing here. And this is going to be our torch dot soft. I've already forgot how they spell it. Is it capital or is it not capital? It's not capital. Okay. All right, and then I'm just gonna make up some weight, which is actually what this is right here. So we'll just say a tensor, cause I think it needs to be that. So we'll make that easier. So we'll say weights, and then we'll say this is gonna be a tensor. Oh, I see what I did here. I deleted that R. All right, so we have our tensor, and then we're gonna put some weights. What weights do I want? I need 2, I think. So we're just gonna put 0.1, and then we'll say, what's another good one? I don't know, 0.37, how about that? All right, so we're gonna put our weights in here. And I'm not gonna do the dimension thing right now. I'm just gonna keep that as is, because I wanna see, like, what is it really doing? And then we'll say a D, we'll just copy. Shit, how do you copy the line? I forget how you fucking copy. Fuck. Oh, well, I'll just do this. It's like I can go into visual mode right quick. I can do it that way. All right, so now we have our width -1. Cool, so now we have our weights. Dim equal -1, and then I want to also print that as well. Okay, so you got a tensor, but you expected a tensor, which we get, an int for the dimension, which you do. Oh, I guess it wants the torch D type. I don't know. How the fuck would I know the D type? And this is new? No, that can't be right. I was just looking at the doc. It didn't say that. It says something completely different. It says I just need to give a dimension. I'm calling the wrong one, obviously. I must be calling the wrong one. Softmax. Yeah, it's the wrong. Wait, Torch NN Softmax. Okay, maybe it's not the NN. Maybe there's another Softmax in here somewhere. They all seem to be part of NN. Okay, well, huh. All right, well, I'm a little confused by this one. So they are doing that filter that I said they were probably doing right here. This mask. It's just that because this is Python, like it's all imperative. Like you all, yeah, like there you can just do a filter. That also works. Just call filter, but that's fine. All right, combine process tokens with unprocessed ones. Process tokens plus. All right. So I wonder if this is times or if this is a convolution. Do they have a special? Do they have special syntax for convolutions in PyTorch? Let's see. Oops, wrong thing. Oh, no, I have a function. It's called conv2D. But I imagine they should have another one too. Like, obviously you can do more than just two-dimensional convolutions. Or maybe they're forcing you to do it piecewise for whatever reason, which would be dumb. Convolution. I can spell. Convolutionary. All right, there we are. Convolutionary. 1D, 2D, 3D, transpose, 1D, 2D, 3D. Huh. I wonder if like you have to, I forget, it's a technique that you can do where like if you have like a multi-dimensional thing, like you can, assuming that actually this is linear algebra, it has to be the case. I think that the convolutions of two functions is the same as the convolution of a function plus the convolution of another function. Or what I'm trying to say is, I think it's associative, or is it what's the word? There's a word that we use in math. I'm not a mathematician, so I don't know it. But there's a word, is it associativity or something like that? Where essentially this right here, so let's say I have conv of A. Yeah, conv of A. And then I say plus conv of B. That's effectively the same as conv A plus B, right, like that. I want to say this is associative. Then there's the other one, which it starts with a C. For some reason, I always think of it as communism. It's like it's communism. It's not that. Oh gosh, communicative something. Communicative, something like that. Effectively, it's this right here, where you can have like conv A is, and then we can say like conv B plus C, something like that. Basically, you can move around the parentheses. Is effectively what that means. I think that's community committed. One of you has to know. There are 11 people here. Someone has to know what it's called. It starts with a C. Come something. Community committed to something. Communism. Community math. How about that? Committed. We can see if we can figure it out. Communism. Property math. Community. That's what it is. This is it. Cumulative. I can't say this word for shit. How do you say this word? Commutative. Yeah, that word. This word. It's that. So because of that, maybe that's why there's only like a 1D, 2D, 3D. Maybe, I don't know. Obviously, I don't know what I'm talking about. I've never used this. All right, let's go back to this dude's code. See if there's anything here I don't understand. Other than there was something that I don't like. I don't know why this is called BSD. Other than maybe in the paper it's BSD. Maybe. Do I know how that paper opened? Now we can close a few things. No, this isn't the paper either. Here we are. Like, what variable is D? Or do they have like a cleaned up model at the end of this with just the math things? No, they don't. All right, so this S, I'm going to assume that this S corresponds to this S right here. I just saw it. Where was it? Here. I'm assuming that it corresponds to this S because he's asking for the shape. And I know that S has something to do with the length of one of the inputs, I think. He defined these somewhere. Where are they at? Is it here? Suppose we have token embedding sensing. Yeah. Here we are. In a sequence of length S. So S isn't, I don't like this. S isn't the sequence itself, even though that would make sense since it's called sequence. It's the length of that. Okay, so this shape right here, that's what this is doing here. Maybe I should show it. Maybe just make it even clearer. Get out of, how do I keep getting in visual mode? I don't understand. I'm gonna delete. Actually, we're gonna delete all of this. Fuck this. We don't need any of it. And we're just gonna do a shape right here. Oh, whoa. No. I don't know what this is. What? Wait. How in the fuck did this happen? That was an accident. Okay. What is this? Wait. NN doesn't have a shape. Okay, so NN isn't what I thought it was, unless NN has some properties on it that I don't know about. Obviously, I don't have syntax completion, so I don't know. I don't know. I have to go look at the docs. Like a freaking plebeian. Let's go do it though. All right, so let's look for shape. It's not in here. Okay. All right, so that's why I can't do it. Turns out NN doesn't have a shape, but I would have expected to be able to get to any of my layers. Let's see if I can get, let's see that. How do I get to a layer? Linear layers. Nah. All right, I wonder if I can just index into it. Yeah, let's try that. Let's index into A0. See what this returns. Linear object is not subscriptable. Okay. Okay. All right. So apparently an NN isn't what I thought it was. I thought an NN was this right here. I'm thinking from a data perspective. In my mind, I'm thinking that an NN is going to be something like this. It's a, oops, like you're going to have a bunch of these right here. Come on now, right? So I'm thinking that this is what an NNN is, or an NN, I'm sorry, a neural network. And why do I think it's that? Well, I'm thinking that this right here, I mean, when I've implemented these myself, you know, I implement all of these as just vectors, right? So a neural network would just be a collection of vectors, right? This first one here, so this would be your input, your hidden layer 1, hidden layer 2 through N, up into your output layer here. This is why I was like, let me just see if I can index into it, but apparently I can't do that. So we got to figure out, how does whatever this thing is work? Like, how do I actually get to the data in this neural net? All right, so it's none of these, which is interesting. I wonder if there's a shape function on here. There's a reshape, but I don't see a shape function or property. Does shape even exist? It would be very interesting if shape doesn't exist, because I mean, when I was doing this in the past, like, the shape of your vectors or your tensors, whatever you want to call them, I'll call them just straight up matrices or arrays. The shape of those are incredibly important. It's so important, in fact, that you can probably like not even know what you're doing and still build this shit, just so long as you you know the shapes of things. And what I mean by shape is like this. So let's say that I have a vector. Let's say I have a column vector, right? So I have a column vector like so, right? Well, if I wanted to do something with it, like some type of math, well, the other thing would have to be something like this, right? And then I can do something, you know, then I can make some magic happen. But if this case isn't met, then like I can't just do it, right? Now I can do something like this, where it's like, let's say I have this thing, a scale, let's say I have a scalar value, this 5 here. What I can do is, let's say that I have this matrix over here, or this row vector. So we'll have like 0, 1, I don't know, 4. How about that? Like I can multiply this, and we'll use, I don't like using this because this is this is overloaded. This is technically the character you use for convolution in math. But for whatever reason, we use this to mean multiplication on a computer, which is interesting. But anyway, if I were to do this, I would get 0, 5, and 20, right? I can do this, right? I can do this all day long. I can even do this right here. Let's say I have like 1, 5. So, you know, my shape is 1, 5, and then like this other thing, it has a shape of 5, 15. Well, if I were to do some type of operation on this, what I would get is a 1 by 15 vector. All right. There are rules for all of these things. I mean, part of it is linear algebra. Part of it is just like, I'm pretty sure they have, I don't want to say I'm pretty sure, because I've never used this. I've never even like used their docs before until just a few minutes ago. So I don't know if they have it, but I'm gonna assume that they do. Hopefully. Okay, so wait, tensor.shape. Okay, so NN must not create tensors. I think this is so far. I think I've come to that conclusion. Let's make this just A and see what this is again. I forgot. Okay, linear. Okay, all right. I guess that makes sense. It's not a tensor. So, I mean, I don't really want to just here. I'll do this just for y'all, I guess. You know, it doesn't really matter to me. If I do this right here, let's say if I just do this empty right here with what they're doing, where I'm going to create a n-dimensional, a 3x4x5 matrix of no values. I'm surprised that I can do empty and not zeros. That's what I would expect to do is zeros here. We'll call this E for now. And then we'll also print the shape of E, which should just be this. Should just be that. Oops. Wait. Whoa. What just happened? Okay, all right, fine. I don't know what just happened with that. But here you are, right? So you see here that we get this 3, 4, 5. That is the shape, right? So why is the shape important? Well, because we're doing matrix math. Like we're doing linear algebra, and like these things need to match. You see here that this empty, it created this 3, 4, 5, and it actually did it. You know, so we have 3 of these things, which each have 4 items in it with 4 whatever columns or rows or whatever words you want to use in it. I thought there was a 0, so maybe that's in the thing that I know, because I've only used zeros, and I think that's NumPy. NumPy has that, right? Let's see. So that NumPy, and then we'll say zeros. Yeah, it's NumPy that I'm thinking of. Yeah, so looks like PyTorch has their own version of NumPy, I guess, maybe. Any of you who are watching, have y'all used PyTorch at all? Do y'all know anything? Do y'all know much about PyTorch? All right, threshold, top K values. All right, this is cool. They just have a function that can give you the top K values. That's dope. Threshold, top K values. I'm not even gonna lie. I don't know what -1 means when it comes to list comprehensions. You know what? I think that means go backwards. At least that's what I would guess. Let's see if I'm right. Assessing the last element of the list or sequence. I was close. It is going backwards, but like all right, fine. It does what I thought it was doing. All right, cool. Now that I know something, we'll go back to that code. All right, in our threshold, we're gonna get our last one. We're gonna get the end value. And then from that end value, we calculate our threshold from the actual values. Then we're gonna create our mask, which is literally just a Boolean expression. And then we're filtering. That's literally what this is. All of this is filtering. It's just freaking dumb. Oh, actually, no, this is it. Oh wait. If this is all you have to do to filter in Python, I can see why people like it. Like you don't have to do this like map or filter and then pass this callback. It's just kind of built in. That's kind of cool, I guess. Select the token size. Dot size. Oh, okay, size. Okay, so you have to tell it which dimension, I think, because this selected tokens has to be multi-dimensional. So we're gonna go on the first dimension if it's greater than 0. Process tokens, sub I, like, okay. So wherever this was indexed to, that's where we're gonna do our computation. I don't know what squeeze does, but I do know that this is where we're doing that computation. So this is where we're getting the advantage of, hey, we've just assigned this work to this particular like compute module. This is what's doing that magic here. Obviously, there's a function that's that determines the routing, but this is what ultimately controls all of that. Combines process tokens on processed ones. Now this part, like, I really don't know what this is doing. I'm not even gonna lie. This is outside of my knowledge of of everything. I don't know what this is. I've never even seen unsqueeze. Like, what the hell is unsqueeze? Is that PyTorch? Oh, I guess it is. It is PyTorch. Returns a new tensor with a dimension of size 1 inserted at the specified position. Wait. Returns a new tensor with a dimension of size 1 inserted at the specified position. Give me a second. I got it. I don't know if I understand this. Oh, wait a minute. Wait. No. Never mind. Maybe I do understand this. Yes, I do understand this. Okay. All right. So it looks like if given a row vector and I do along the zeros, like that dimension 0, I'm going to get back that same thing. But however, if I do this 1 on the second dimension, or I guess any subsequent dimensions, it's going to give it to me in that dimension. So I guess it's not a pivot table, but it seems to be like a pivot. It's behaving like that because we just went from a row to a column. But I don't understand why we wouldn't just use a transpose. A dim value within the range, negative input dot dim minus 1. Wait, negative. So whatever the dimensions are, negative minus 1. And then the input dimension plus 1 can be used. Negative dimensions will correspond to unsqueeze applied to dim equals dim plus input dim plus 1. Okay. Like, I'm trying to figure out how is this different from transpose? Or is that transpose? No, they have a transpose. All right. Let's see how unsqueeze is different. I don't know how this is different from transpose. Oops. Squeeze different from transpose. All right, let's see. Unsqueeze adds a new dimension to the tensor, increasing the dimensionality. Okay, so this is how this is different. All right, so if you have a 1D tensor of shape n, and you apply unsqueeze at dimension 0, you get a 2D tensor of shape 1n. Oh, okay, all right. I think that's what I was seeing here. It didn't make sense. It was just empty right there. See that space? But then I looked at that space right here. I was like, oh, well, maybe that's it, but maybe not. Okay, and you apply unsqueeze, and you get 2D. Okay, it doesn't rearrange the tensor's elements, but it changes its shape by adding. Okay, so it's changing the shape. Whereas transpose is actually like it's literally you're flipping it effectively. Okay, all right, fine. All right, so I learned something. That's the one thing that I don't fully understand, which is this little bit right here. But yeah, you know what? Let's have ChatGPT tell me what that means. Wait, did I close ChatGPT? Oh, okay. All right, so we're doing element wise. Okay. Select. Wait. How's it getting all this from just that? Wait, it's giving me too much stuff for just this. I only want to know this. It's giving me shit that doesn't matter. But all right, whatever. I'll read it. So our selected mask. Yeah, it's saying what it likely is. Yeah. Unsqueeze. Add a new dimension. And -1 specifies that this new dimension is added at the last position. Oh. So this is effectively doing something that I used to do in this thing called pandas, where if you had a data frame and you had another data frame, you can add them together and you get a new data frame of that size. This almost seems like you can expand the tensor, whatever you want to call it. I'm gonna call it data frame matrix. You can increase its dimensionality by 1. That's what it seems. That's what seems to be the case. It's almost as if we're like, hey, the output, let's add it to the end, but we first have to create like a position to put those values. That's what it almost feels like. All right, so for instance, if selected wait, what is this? Is that not? Is this not in all right. What is it not? Oh, it's bitwise not. Okay. All right. Whoa. Wait. What is this thing returning? We're doing a bitwise operation on a Boolean expression. For instance, if whatever this is of shape nm after unsqueeze will be nm1. 2x.d type. This changes the data type of the tensor mass out of the x's. Okay. Essential when performing tensor. All right. X times whatever that is. This multiplies x with the inverted, unsqueezed, and type converted selected mask. Okay, so we're doing this for types. I didn't know Python had types. The multiplication is element wise, and due to broadcasting, thanks to unsqueeze, it aligns the last dimension of the mask with the course. I wonder if that's why they're doing it. It's specifically for broadcasting. Process tokens. Finally, result of the tensor is added to process token, element wise. It's adding the process token to the modified version of X, but the modified is controlled by the selected mask. Okay. All right. So this is his implementation. Let's see what happens. Let's just use it. Let's copy his code. And just dump it in. test name, whatever has py. Where are the tests? Oh, here. Wait. Huh? Find inside of tests. Okay, there are no tests. At least I don't have them. Maybe. I don't see any tests. Let's see. Tests. Yeah, there ain't no tests in here. All right. So we're going to create a MOD. Excuse me. Oops. Oh, fuck. How did that happen? What was it? MOD capacity and block. Wait. What the hell is a block? I've already forgotten what the hell block is. I'll just put some numbers in and see what happens. So we're gonna put in 4 and 5, I guess. I don't know, just see what happens. Print it. I didn't mean to do that, but fine. It's fine. Int object has no attribute dim. All right, that didn't work. What if? Wait, it wants a neural net, right? Like, yeah. Let's wait. Does it want a neural net? I've already forgotten. And then module. All right, I'm going to assume that I can just do this NN thing right here. We'll say, wait, is it NN? Yeah, I'm going to assume that I can do NN dot linear or something like that. Oops. Dot linear, linear that, and we'll say 2, 1, whatever that is. See if this has any effect. If it's not obvious, I don't know how to use this. Yeah, that's, wait, oh shit, wrong one. MOD linear, type here. Missing 1 required positional argument, block, okay. Let's try to figure out what the hell block is. I really don't know what block is. But I'm gonna just say 1, how about that? Just see what happens. Int object has no, okay, so then block is obviously not integer. It needs to be something that has a dimension. So I want to say that that can also be a tensor. I think tensors have dimensions, if I'm not mistaken, maybe, hopefully, we'll see. So we'll say tensor, like so, and then we'll just say it has 1 element 1. All right, empty. Argument size failed to unpack the object at position 2 with error. Yeah. This is actually my fault. See here, this 2, 1, and then I'm like get tensor. I want tensor 1. Well, this thing right here needs to match. So let's make it somewhat match. All right. Now we get something else empty. What did I give it? Did I not give it a tuple? Does it want that? Is that why it's tripping? No module name torch. Wait, seriously? Oh, okay. I'm tripping. All right. I don't know. Who knows? What I think I'm going to end up having to do is read this paper a little bit more in depth and also wait, also see if there are any other papers, like people who've done other dives on it, basically. Yeah, so I'm gonna say it's enough of that paper. No, we did learn a little bit about a new method, a new architecture at least. So really the main part that's new, like all this other shit's mostly the same. The main part that's new is just the predictor. I don't know if I like calling it a predictor. Let's call it a router that uses the same techniques for creating a prediction to determine what particular block should perform the computation. Yeah, all in all, yeah, that's something good to know. All right, cool. So I've been streaming for about 2 hours and talking mostly nonstop to mostly silence. Do any of you all have anything to say? Except for you folks who are on Twitter. I do realize that, like, you all who are on Twitter, y'all can't really talk to me. And if y'all can, you should try it. Like, type something. I want to see if it'll go somewhere. Like, I don't think I'll see it, but maybe I will. Who knows? All right, so I'm not about to work on the bot mainly because I've already been doing this for 2 hours, but I will probably work on it next week. I've already gotten most of the GitHub application, like all of that stuff that's been integrated. Now this is mostly just like getting in a position where I can get it merged and then up into production. And I'm gonna move on to the next feature, which, you know, I could do some more stuff on the GitHub side, but I'm kind of anxious to get into the AI feature set that I had intended to build, specifically around doing like search, right? So I'm using AI to enable search a video using natural language. So that's what I want to start putting a little bit more time into. There are some other, like, you know, AI things that I need to kind of brush up on that I think I'm gonna use, specifically in RAG, which is a retrieval augmented generator. And I don't know if I want to implement one from scratch, but maybe I will. I do think there are services that you can use that, you know, give you this stuff for you, and maybe I'll use it if it if it saves me a lot of time, which I imagine it would, because I wouldn't have to worry about where do I store these documents, you know, or which vector database do I use. Like, these are questions that I wouldn't have to really worry about if I'm doing this all on my own. I'm sorry, if I choose to use a service provider. I'm sorry, yeah. So, like, I don't have to worry about setting my own Postgres server and make sure that's right. I don't have to worry about permissioning. I don't have to worry about anything. I just worry about how do I integrate with whatever that platform is, which, you know, that could be difficult too. Like, that's comes with its own set of problems. I seem to be missing a camera. Nowhere. I only see 3 of them. I think I may have left my other camera in the car. I was like, I have photos that I thought these were it. I'm like, I have photos I can be editing. I do have some photos. Not photos. Lightroom. Actually, I don't want to go. I don't want to do that. I want to look at photos. All right. Well, I guess I'm gonna go. Nobody's saying anything, so I'm gonna assume that nobody wants to talk, which is cool. I don't want to talk either. Y'all have a good rest of the day. Enjoy the rest of the weekend. Peace.